Hi and welcome to our fifth video. Today we start talking about horizontal curve design. In the previous classes, we pretty much went over vertical curve design. We learned their most important characteristics, how to design them, and how to relate their lengths to stopping side distance on both sag and vertical curves. Today, we switch gears and we start talking about horizontal curves. We get to know some of their main characteristics and essentially how to design them, how to find the radius and other features of these curves. So here I'm showing you a horizontal curve. This is what you are mostly dealing with on a daily based driving that you have. So you're driving and the road is turning to right or to left, and you turn the wheels to keep your vehicle on the road. So here you can see that um, here the vehicle has to make a right turn, and then after some time follows the road with making a left turn lane if you are on this side of the road, and of course the opposite if you are on the opposing traffic. So it is very important to keep in mind that whenever we talk about horizontal curve, we are looking at the road the way that we look at a map. So we are looking from above, as I'm showing um, with this graph. So what you see um, is gonna be something like this in the direction that the traffic goes. So you go and you make a right turn, and then you follow with a left turn. This is different than the way that we were looking at vertical curves. We were looking at vertical curves from the side of the road, so we could see that the road is going up or going down. So from the viewpoint that we were looking at vertical curves, we couldn't see the horizontal curves, right? So you couldn't say if there is a right turn on the road or a left turn on the road. You just see if the road is going up or down. And pretty much is the same here. So we are looking the way that we are looking at a map. So you cannot say if the elevation of the road is changing, but you can say if the road has a right turn or a left turn. So I want to talk about the critical design feature of horizontal curves. And really what they do is that they transition the roadway between two straight sections. What do we mean by that? So let's say your road is going this way, and then at some point the road is gonna go this way. The horizontal curve is what creates a transition from going on this direction to the other direction without you have to go through this point, like what happens at an intersection, and then you have to make a sharp turn. So rather than doing that, you are going straight and you transition to turning right, and by the end of that curve you are on the other piece of the road. If we didn't have a horizontal curve here, what would happen? The car that was driving was going here, and at this point had to make a sharp right turn. So when you are driving on a horizontal curve, vehicle cornering capabilities are very important. So think about it as if you are driving a sport car versus driving SUV. If your car has a good cornering capability, you can probably go into let's say right turn curve much faster compared to SUV that is heavy, it is high, and it is a higher center of gravity, and when it wants to go through that curve, it needs to go through the curve much slower. So on the next slide, I want to show some of the forces that act on a vehicle, and actually I'm going to show a motorcycle when that vehicle or that motorcycle is going through a corner. So let's take a look at this. Let's assume that this green circle that I have here is our vehicle, okay? And it's going through this curve. So we know that in such a condition we have centripetal force that becomes active, and you can see the centripetal force here, and we know that the amount of the centripetal force is equal to W over G into V square over RV. What is W? W is the weight of the vehicle that we have, or the weight of the object. G is the gravitational acceleration. V is the speed of the object, and R sub V is the radius of the curve. So let's take a look at the motorcycle now. So here you can see that we have the centripetal force towards the center. You can see that we have the friction force that is trying to help, or that is trying to maintain the vehicle on the road. So what happens if the coefficient of friction is low? You cannot maintain a high speed when you are going through this curve, because F sub F is going to be small. What's going to happen if the coefficient of side friction is high? You can go through this curve with a faster speed, right? If your tires are really good, if the pavement is really good, you can go through this curve faster. Is there anything else in your mind that can contribute to you going faster in this curve? Think about the elevation or super elevation of the road. So if you are driving on the road and the road has a slope like this, and you can imagine this like what you see in NASCAR races. So you see that the track is really sloped and it has a high super elevation. So this force is gonna maintain you or push you toward the center of the curve, and if you have this, you have a higher, you can go through the curve much faster. So here the curve is like this. So let's take a look at this car. This car is going on a circle, and if you want to imagine it, when this car is coming out of your screen towards you, it goes towards your left hand side, okay? So the car is turning right, is making a right turn, but when it comes out towards you, it's turning towards your left hand, okay? So the car is going around a curve like this. So here you see R sub V. This is the radius of the curve. We also know that the roadway has a slope. That slope is shown by E, okay, and the angle is alpha, and that angle also is shown here. This is also alpha, right? Here I'm showing you the weight, and we have the normal and also the horizontal components of the weight. We show the normal component by Wn, the horizontal component by W sub P. So what is the value of Wn? We know that this angle is also alpha, right? So Wn, we know that it is equal to W into cosine of alpha. Wp is equal to W in sine alpha. Here we show the centripetal force. So that's F sub C. This angle is also alpha. And we know that F sub Cp is equal to F into cosine of alpha, and F sub Cn is equal to F C into sine alpha. So you also see the friction, or F sub F, here. So what I want to do in the next slide is that I want to work on the forces that this vehicle is experiencing along this plane that is horizontal to the super elevation, or horizontal with the road, the way that we are looking at it. And based on that, I want to get to an equation that is gonna tell us what should RV be based on parameters such as super elevation, speed, and other things that we have here. So I'm not gonna go into everything that you see on this slide, but this is for you here so that you exactly know what is the definition of each of these parameters. So let's start with the first equation that we can write down. So we can write down W sub P plus F sub F is equal to F sub Cp. So this is when we look at all forces that we had on this plane. Okay, so we know that F sub F, or side friction force, is equal to the coefficient of side friction, or F sub S, multiplied by the normal forces that the vehicle is experiencing, right? And the normal force, if you remember, we had W, and we also had Wn, and also we had F sub Cn. So the normal force that we have here is equal to F sub Cn plus Wn. Okay, so I have that. And if you multiply that by F sub S, that is gonna be our friction force. Okay, now I'm gonna go back into this plane, and let's think about other forces that we have. So we have F sub F, so I have that, the value of that, and I have Wp, okay, and the summation of these two is gonna be equal to the forces that the vehicle is experiencing, right, on this plane. So what I'm gonna have is W sine of alpha, so this is WP. Then I have this term, which is F sub S into Wn, or W cosine of alpha, and F sub Cn, or W into V square over G, or V into sine of alpha. So this is F sub Cn. And this should be equal to F sub Cp, which is W into V square over G into RV into cosine of alpha. So what I'm going to do here now is that I'm going to start working on this equation and simplify things. Okay, let's do that in the next slide. So we divide both sides of that equation by W into cosine alpha. So if you do that, we are going to have tangent of alpha plus F sub S equal to V square over G into RV into 1 minus F sub S into tangent of alpha. Okay? So the first thing that we want to work with is that tangent of alpha, we call it as super elevation of the curve, and we show it by E. But actually we define E as 100 into tangent of alpha. Okay, so keep that in mind. We also here have F sub S into tangent of alpha. F sub S, friction of coefficient of side friction, is a small value, it's at 0.15. Tangent of alpha is also a small value. As a result of that, this value is very close to 0, so we just assume it is 0, so we ignore it here. And then in this side, rather than putting tangent of alpha, I'm gonna put E over 100. Okay, so if you do that and you solve this equation, let's see, let me do a little bit of that. So rather than tangent of alpha, I'm gonna have E over 100 plus F sub S is equal to V square into G R sub V 1 minus F sub S tangent of alpha, and I said that this is 0, right? So I just remove it from here. So I'm gonna have something like this, so I can remove this whole thing now. Okay, and now I want to solve for R sub V. So what is R sub V? R sub V is equal to V square divided by, so I'm gonna have G here, into E over 100 plus F sub S. So if you look at what I have here, it's pretty much identical to that equation. So what this equation tells me is that if I know what is the speed that the vehicle is traveling at, if I know the coefficient of gravitational force, if I know the coefficient of side friction, and if I know the super elevation, then I will have the maximum radius that I can have for a curve. So let's go through this example, and hopefully by going through this example we learn this equation much better. So we have a roadway that is being designed for a speed of 70 miles per hour. So our V is equal to 70 miles per hour. At one horizontal curve, it is known that the super elevation is 8%. So my E is 8. And the coefficient of side friction is 1. So F sub S is 0.1, not 1, it's 0.1. Determine the minimum radius of curve that will provide for safe vehicle operation. So it's asking for R sub V. So what I would like for you to do is to pause the video here, go through this example, don't watch the video before you have your final answer, and then unpause and take a look at the solution. Okay, let's do that. Please pause. Okay, now that you have the answer, let's go through the solution and see what you've done. Okay, so we know that R sub V is equal to V square over G into F sub S plus E over 100. Okay, so pretty much what you need to do is that you need to plug the numbers that we had into this equation and get the answer. So I'm just gonna put 70 raised to the power of 2. Then I'm gonna put G here, right? And then I multiply by F sub S, which was 0.1. Then I add 8% and I divide it by 100. I put all of these into the equation, to the calculator, and I get the results, right? If you do that, the number that you get is gonna be wrong, unless you are using the right units or consistent units for speed and the coefficient of gravitational force. Okay. So how do we do that? So 70, you need to convert it to foot per second if you are using feet per second for feet per second square for G. So here the speed is 70, I multiply it by 5280 and I divide it by 3600. Why? 5280 converts a mile to feet and 3600 converts hour to seconds. So as a result of that, this speed that I have here now is in feet per second. Make sure that you have this conversion inside the parentheses, okay? Then I divide it by 32.2 into 0.1 into 8 over 100. So if you do the calculation and you have all the numbers right and there is no calculation error, the radius that you need for this horizontal curve is 1819.4 feet. 1819. In the previous example, we saw how we can determine R sub V based on speed and super elevation and other parameters that we have, such as F sub S. But I want you for some time to think about designing the road. So really there are several parameters that you are working with, and they are influencing one another. So you have super elevation, you have the radius, you have speed, maximum speed or speed limit that you want to allow vehicles to travel at that speed on the road. You have um, the coefficient of side friction. Maybe you don't have much control on that, but maybe you have some based on the pavement that you put there, right? So how do you select these values? And it's quite challenging to do so. Now, among all of these values, probably we have the lowest control on f sub s, and we cannot make a lot of changes there. But maybe you can put a lot of super elevation on a road so that your radius is smaller, or you increase the radius so that the super elevation is lower, or change the speed limit, right? Now think about super elevation by itself. So this is how much lateral slope you have on the road. Think about what is going to happen if your super elevation is too high. If the super elevation is too high and you are making a turning movement, maybe let's say you are going and you're turning left. If the super elevation is too high, it's going to push you towards the center of the curve, right? So you may feel something like oversteering. Or also think about it when the road is covered with ice. If the super elevation is too high, your vehicle may slide towards the center of the curve, right? What if the super elevation is too small? What's going to happen in that condition? Well, you need to have a very big radius, right? Or you need to reduce the speed. Otherwise, the vehicle is gonna fly out of the curve. So you're gonna have understeering, right? So just read through these bullets that I have here. High rates of super elevation can cause vehicle steering problem. These are mostly oversteering, right? So when you are turning, you go towards the center of the curve. In icy conditions, vehicles that are traveling less than the design speed, or maybe they are stopped or going very slow, they could slide inward of the curve by gravitational forces. And if you have a low rate of super elevation, it's hard to go through the curve. Either the speed needs to be low, or the radius needs to be large, or you're going to have understeering. So selecting a good combination of these parameters is really a design challenge. And AASHTO guidelines have selected appropriate values for the combination of E and coefficient of side friction, because if the coefficient of side friction is low and you have a high E, now your vehicle may go inside the curve in icy condition, right? And so there is a good combination of these that we are going to see them in the next slide. So in this table, what you see is the design speed. So you see the design speed here. In each part of this table, you see a certain number for the super elevation, or certain value for super elevation. And you can see that it starts from 4, goes to 6, 8, 10, and 12. Okay? And so if you have a certain super elevation, let's say your super elevation is 6, then you know that you are on this side of the table. The table also gives you limiting values for f sub s. Okay? So if your speed is, for example, 40 miles per hour with super elevation of 6, we know that we are on this line. So what this tells us is that your f sub s at most is going to be 0.16, and the calculated radius is 48.4, and rounded radius is 485. So rather than the need to go through the equation, pretty much if you know your speed, your super elevation, this table is going to tell you what is the appropriate f sub s and what is going to be the calculated and the design value for the radius or r sub v. And it does that for 4, 6, 8, 10, and 12% super elevations. So on this slide, we are looking at different horizontal curves. We have the simple curve. Here I have a tangent. I have another tangent. And I connect them to each other with a circle. And that's it. I can have excuse me, I can have a reverse curve. So here, if we are traveling this way, I first make a right turn. And as soon as I'm done with that, I'm going to start a left turn. So I have a tangent here, and two curves. You can have a compound curve. So you have a tangent here, and then you connect these two with two different curves. This is curve 1, circle 1, and this is circle 2. And finally, we can have a spiral. So you have the tangent here, you have a circle here, and you have your tangent here, right? And in your way to go from this tangent to this one, you go through a spiral, then through a circle, and then through another spiral. And these spirals are parabolas that connect the tangent to the circle. And the reason that we use a parabola is that if you directly connect a tangent to a circle, like what we have here, you're gonna have to instantly turn the steering wheel at this point. But the spiral provides us with a smooth transition from this curvature of a tangent line. So there is a curvature of 0, and then we smoothly transition to the curvature that we have here, that is the curvature of this radius, or this is the circle. And so as a result of this parabola, you have a smooth transition and you don't need to turn the steering wheel abruptly. So our focus in this class is on simple circular curve. So we have a single curve and we have a constant radius to go through that curve. Okay, let's focus on this horizontal curve here. And I want to start with this angle. So this angle is delta, which is identical to this angle here. This is also delta. Here I'm showing you a tangent and another tangent, and we want to transition from one to the other one using this circular curve. So PC is the point of curvature, PT is the point of tangent. So PC is where the curve starts, PT is where the curve ends or the tangent starts, and PI is point of intersection, when the two tangents intersect, yeah. So the length of the curve, unlike vertical curves, is measured on the curve, and we show it with L. If you remember, the length of vertical curves was measured along the horizontal plane. That's not the case here. We also will see how to determine this length, that we call it M, how to determine this length, that we call it E, and how to determine T, or the distance between PC and PI along this tangent. Okay, so we start with the degree of the curve, and here you see the equation, and this directly comes from the definition of degree of the curve. So let's read it through. Degree of a curve is the angle subtended by 100 feet arc along the horizontal curve. So if you walk on the curve for 100 feet, how much angle is changed? That is called the degree of the curve. And this equation here is going to help you to find it. So I would like for you to think about how you can get this equation from this definition. Okay, it's quite interesting to figure this out, and I want you to do it on your own. T is equal to R into tangent of delta over 2. How can we do that? So if you focus on this triangle here that I'm showing, in this triangle, tangent of this angle, which is delta over 2, is equal to this length, which is T, divided by this length, which is R. Sorry, this length, which is R. So as a result of that, T is equal to R into tangent of delta over 2. So how do we determine E? E is equal to R into 1 over cosine of delta over 2 minus 1. So if you think about E, E is equal to this length that I want to call it X. So E is equal to X minus this length, and this length is R, right? So let's see what is X. If you want to find X, you can look into the previous triangle that I showed, and you know that cosine of delta over 2 is equal to r divided by x. As a result of that, x is r divided by cosine of delta over 2. So if you just substitute x with this value here, you're going to have e equal to r over cosine of delta over 2 minus r, which is equal to r into 1 over cosine of delta over 2 minus 1. This is the equation that I have here. I'm going to delete this, erase this, so that we have room for other equations. Okay. Our next equation is m, which is equal to r into 1 minus cosine of delta over 2. So if you just do the same thing, you'll be able to find m. This time you need to know that m is equal to this distance, which is r, minus this distance. So I call this distance y now. So y is going to be equal to r into cosine of delta 2 if you look into this rectangle. And then if you just do the math, you're going to get this equation that I have there. And finally, L is going to be equal to pi over 180 into R into delta. So I'm going to stop at this point. And actually, let me go one more slide forward, and I stop there. So in this slide, you have the definition of all parameters that we saw on the previous slide. So I'm going to stop here, and in the next class, we are going to start with an example problem that goes through these equations that we just learned.